Barry from Barry Science Lab, and today we're going to be looking at a very weird function. Okay, so here's the deal with this function, right? So this function has a non-zero derivative at x equals 0, right? And we'll prove this. So this function is defined everywhere and always differentiable. It's C1. And lastly, this function is not injective. Actually, it's never injective. So, does this go against the inverse function theorem? Well, we'll find out next time, but first of all, let's prove these three assertions. Alright, so first of all, this guy, right over here, f prime of 0 is equal to 1. How do we prove that? Well, f prime of x is going to look something like this, and we're going to have to use the product rule on this guy. So we're going to get 4x sine of 1 over x, and then, well, we're going to have to do something messy with this. Essentially, we're going to have to take this out, take the derivative of that. So we're going to have plus 2x squared multiplied by what? Negative 1 over x squared times cosine of 1 over x, which cancels this out and gives us 1 minus 2 cosine 1 over x plus 4x sine 1 over x, which means clearly it's not too approachable at x equals 0, right? Because we have this giant glaring thing right here. But we can bound it, right? I mean, just think about it. This x helps so much. Why? Because we know sine of 1 over x is always in between 1 and negative 1. Hence, 4x sine of 1 over x is always between 4x and negative 4x. And of course, we can just use the squeeze theorem from there to declare that since this approaches 0 as x equals 0, as x approaches 0 and this approaches 0 as x approaches 0, the guy in the middle has to be sandwiched in between them. And so, that means that as x approaches 0, 4x sine of 1 over x is going to approach 0. Now, the cosine 1 over x is also a little bit tricky until, you realize what that's actually going to look like. So, how do we know this is going to approach 1? We have this guy right over here, and that's just a phase shift of sine. So how do we get past this problem? Well, you can also attempt to do this another way, by just taking the derivative of this function. Now this function, what's the derivative as x approaches 0? Well, it's enveloped by 2x squared and negative 2x squared. Well, no, actually it doesn't look like that. I'd say it probably looks like and now you have to realize, oh, this actually goes sort of downward. Sorry. And now you have to realize something. Because it's getting squished, the derivatives don't have the chance to get funked out to an outrageous degree. The derivative is getting squished between x squared, whose derivative approaches 0, and negative x squared, whose derivative approaches 0, which implies, naturally, that this derivative by the squeeze theorem has to be equal to 0. And then, when you add the x term, that derivative is just equal to 1, so by linearity, this is equal to 1. So it's defined in C1. Well, when we look at this guy, we can see that it's continuous over the entire domain. Since 1 over x is continuous over its entire domain, which, keep in mind, the domain doesn't include 0. Sine is continuous, and of course, composing two continuous functions gives you a continuous function over the intersection of their domains. Continuous function by addition. Everything's continuous. We're all good. So the derivative is continuous everywhere. And it's non-injective. What I mean by that is we can't find r is greater than 0 such that that epsilon neighborhood minus r to r, f is injective over this. So, how do we know we can't find it? Well, by the Archimedean principle. More specifically, sine of x. Well, when f prime of x is equal to 0, there are three scenarios that dictate what's happening. Either you've got a minimum, in which case you can clearly show that it's non-injective. You've got a maximum, where you can also clearly show it's non-injective. Or you have a saddle point, also known as an inflection point, where sometimes it actually is injective, like for example 1 equals x cubed. So, this is where f prime prime of x actually changes signs, instead of f prime of x changing signs. So, how do we show that this is true? Well, now, here's what we have to do. We have to look at where x is going to be exceedingly small in an epsilon neighborhood around 0. So we only really have to look at where this has maxima and minima. And that's notably when, what? Saddle points, who knows, even though it actually doesn't have saddle points, keep that in mind, when its derivative is equal to 0. Obviously this can never be equal to 0 since it's 1 over x squared, which implies that it's only when this is equal to 0, and thus when 1 over x is equal to 2n minus 1 pi, or in other words, when x is equal to 1 over 2n minus 1 times top. Wait a second. Yeah, that sounds right. But is it true? Cosine of 1 over x is 0. Oh. I think it's pi over 2. Yeah, pi over 2. Yeah, okay. So it looks something more like this. So we can call it a sequence like that. And by the Archimedean principle, we're kind of just multiplying the sequence 1 over n by a constant and then adding to it, right? Because this is 2 over n times 1 over 2n minus 1. And by the Archimedean principle, the infimum of this is 0, which naturally implies that any r we find that is greater than 0, there exists an element of this set lower than that, and thus in the epsilon neighborhood, which implies that there will always be one of these points inside the neighborhood, but maybe they're all saddle points. Well, then you have to look at where the second derivative, which is going to look a little bit distressing, but you use the product rule again to get what? Well, it's going to be negative again. Okay. Or in other words, so there's only an inflection point if, well, something like this is true. And this is pretty much never true. Yeah, this is not true. So that means that we're never going to find any of these inflection points anyway, right? Because sine of 1 over x is kind of like sine, but the frequency just increases, which means that, of course, when you take the derivative twice, what you're seeing in essence is kind of just sine of 1 over x again. But that has zeros, and those zeros are not equal to the zeros of the cosine of 1 over x function. Thus, that implies that sine of 1 over x has only maxima and minima and no inflection points, which therefore means that it's non-injective over any epsilon neighborhood. So that's it. Thank you everybody for watching.
Very nice.